All right, let's see if that's too blurry. Yeah. There we go. Okay. Might as well write the rest. Okay, so last time we talked about, well, we basically just introduced the complex numbers, from scratch in this kind of informal way. And we talked about functions of complex variables. And now I'm going to introduce the concept of a complex derivative. And we're going to use that to define basically the main object of study in complex analysis, which is the class of analytic functions. And then we'll go ahead and derive something called the Cauchy-Riemann equations, which are a necessary and sort of sufficient condition. You need a little bit extra for analyticity. So without further ado, let's define a complex derivative. So we have a complex, let's say complex valued function f. So f just goes from some domain in the complex numbers out to the complex numbers. We say it's differentiable I should qualify this with at z0, which is a complex number. If the limit as z approaches z0 of f of z minus f of z0 over z minus z0 exists. So that should look familiar. Hopefully we've all taken calculus. This is just the usual limit formula for a derivative, right? But we have to be a little careful because when we're dealing with real numbers, well, we're working on the real line. So here's my 0, infinity, minus infinity, and so on. And when I take the limit as x approaches some number, let's say a, what I mean for the limit to exist is that the limit exists from this direction and also from this direction, and they agree. Well, what do I mean in this case? Here I'm dealing with the complex plane, and I have some point z0. So now I can approach not just from the left and the right. So I could go this way, could go that way. I can also approach from above or diagonally, or I could just kind of spiral in. It's a lot of crazy stuff I could do to get to this point. So the existence of the derivative for a complex valued function is, I would say, a lot stronger than the existence of a derivative for a real function. It's the existence of this limit, it requires a whole lot more. So, but when this thing exists, we say the usual things. We say that f is differentiable. The limit is denoted f prime z0. Sometimes df by dz z0, right? And we call it the complex derivative of f, and usually we'll just call it the derivative. Okay, so that is still a little bit blurry. Let me try to fix that. Okay, there we go. Okay, so maybe just an easy example is in order here. We just take the constant function, then what's our derivative? Well, it's this limit of f of z minus f of z0 over z minus z0. And the numerator is just c minus c. And I've dropped a limit sign, but it doesn't really matter because obviously this thing is 0. Right? Okay, so good news, when you have a constant complex function, its derivative is still zero, just like the real case. Okay. So sometimes it's useful to write the following. Sometimes it's useful to write, delta z, define this quantity to be z minus z0, so that the formula for the derivative at z0 becomes the limit as delta 0 goes to 0 of f of z0 plus delta z minus f of z0 over delta z. So this should also look familiar. I think in your ordinary Calculus 1 course, we would probably replace this delta z with an h. H would be some real number, right? So delta z is some complex number here. And we usually drop that z0 and just write z instead. Okay. So with this form for the limit, it's easier, I think, to tackle this next example, which is a power function. So in this case, we have for the derivative, so what do we expect from the real case? Well, if it's anything like the real case, we'll get this guy, right? So let's work it out. This is the limit as delta z goes to 0 of f of z plus delta z. So that's z plus delta z to the mth power minus z to the m over delta z. And now we invoke the binomial theorem. So binomial theorem tells me that this z plus delta z to the m is the sum from j equals 0 to m. M choose j. Let's do z to the j and delta z to the m minus j. So we can put that in here, and then notice that the mth term is just, so this is m choose m, which is 1. This is z to the m, and this guy becomes 1. So it's just z to the m, which is being subtracted off here. So what we get is the sum from j equals 0 to m minus 1 of m choose j, z to the j, delta z. And how many of these do we have? We have m minus j, and then we subtract one more from the denominator. Okay, so now we can go ahead and take the limit as delta z goes to 0. And well, this will always vanish except for when this exponent is equal to 0. And when does that happen? That happens when j is equal to, did I drop something? No, okay, so that'll happen when j is equal to m minus 1. Yes, okay. So then what we have is the limit, we're taking the limit. This is m choose m minus 1, z to the m minus 1, and m choose m minus 1 is just m. And so again, we get what we expect. So far so good. The complex derivative seems to behave just like the real one. And so we might wonder what the difference is going to be, and we'll get there. But it's worth doing another example first. And this is an example of a function which is not complex differentiable. So remember, this z bar just means, so if z is equal to x plus iy, this is the complex conjugate, which is x minus iy. Right? So here, x and y are both real. Okay, so I claim that this function is not differentiable. Okay, so on the one hand, what we could do is, so what am I going to do? What I'm going to do is I'm gonna take the limit from two different directions, and we will get finite answers. The limit won't diverge, but these answers won't agree with each other. Right? And so this goes back to what I was saying about the complex plane here. Right? We want the limit to exist from any direction, and we want the value of those limits to coincide with each other. So on the one hand, if we take delta z to be real, so let's just call it epsilon, well, then we can go ahead and take this limit, and let's see what we find. We get the limit as, so delta z is epsilon. So this is f of z plus epsilon minus f of z over epsilon. This is the limit as epsilon goes to 0 of, so the complex conjugate of z plus the complex conjugate of epsilon, but epsilon is real, so it's just itself, minus the complex conjugate of z over epsilon, which of course, these guys cancel, and then we get epsilon over epsilon, which is 1, and so this limit is 1. Okay, so now we'll go from, so we went from the real axis towards 0. Now we're going to go from the imaginary axis towards 0. So on the other hand, if delta z is purely imaginary, so again, epsilon is real here, then the limit as epsilon goes to 0 of f of z plus I epsilon minus f of z over I epsilon is, so we do the same thing here. We get complex conjugate of z, and now when we take the complex conjugate of I epsilon, we get a minus I epsilon minus the complex conjugate of z from this guy, and then over I epsilon. And again, we find that the z conjugates cancel, and the I epsilon over the I epsilon, those cancel, and we're left this time with a minus 1. So this is telling me that if this thing were differentiable, then the derivative would be equal to both 1 and minus 1. And so we've reached a contradiction. So the map, or the function that takes a complex variable to its complex conjugate is not differentiable. Okay. So a lot of the usual properties of the complex derivative do still hold. We derived a couple of them. The derivative of constant is 0. Derivative of a power function is, well, the thing that we expect, and the following still holds as well. So if you have a complex function that's differentiable at z0, then it's also continuous. Here's the proof. So it's very simple. Just write f of z. So let's add and subtract this extra term. So all we've done is added 0 here. And now I'm going to multiply by 1 in the following way. Okay. So these are legal moves. I added 0 here. I multiplied this guy by 1 here, right? Just in a creative way. So since we're assuming f is differentiable, this tells me that this difference quotient here will approach the derivative at z0 as z approaches z0. On the other hand, this term is still left over, and as z goes to z0, that surely goes to 0. And so this whole term here will go to 0, and we're left with f of z0. So this tells me that f of z, f of z approaches f of z0 as z goes to z0, which is what it means to be continuous. Okay, so differentiability still implies continuity. That's good. A lot of the usual rules still hold. We have, for example, the product rule. So if we have a derivative of a product, and I mean, the proof is basically exactly the same. We have f of z plus delta z, g of z plus delta z, minus f of z, g of z over delta z. So if you've taken a real analysis course, the proof is almost identical. What you do is you insert this extra term, you add 0 creatively again. That term is this one here. Run out of space. And then we had that other term, f of z, g of z. Okay. And now I'm going to divide this whole thing by delta z. And what this allows me to do is split this into 2 limits. One of f of z plus delta z times g of z plus delta z minus g of z over delta z. So that's the first 2 terms here, plus another limit. And it's going to be these 2 terms here. So we're going to have an f of z plus delta z minus an f of z over delta z, and then there's an extra g of z. Okay, so I assume that both f and g are differentiable. Okay? And so that tells me that, well, this guy just approaches f of z, and this guy approaches the derivative of g. So we get f of z, g prime of z, plus this guy approaches derivative of f, and this guy is just g. So there we go. Again, we have the product rule. Proof is almost identical. So this product rule gives us, I forget what this property gets called. I think it's homogeneity. But if you have a constant multiplying a function and you take the derivative, well, we can now use the product rule to show that this gives us what we would expect from our experience with real analysis. We already showed that this guy was 0, and so we get cf prime of z. So you want to take a derivative, the scalars still factor out. We also have the other half of linearity. We want the derivative of a sum to be the sum of the derivatives. And this one's very easy to show. So that's f of z plus delta z plus g of z plus delta z minus f of z minus g of z over delta z. And then we just split this into two pieces. F of z plus delta z minus f of z over delta z plus the limit as delta z goes to 0 of g of z plus delta z minus g of z over delta z. And then we recognize these things as f prime and g prime. So this plus this is linearity. So we have the product rule, we have linearity, and I'll just say, I'll leave it for homework, the quotient rule also holds. And I'll call that homework. It's a little trickier than the product rule one, but not by a lot. Okay, so the other, well, maybe the most important derivative rule is the chain rule. And luckily, this also still holds. So how does that go again? Well, we suppose that g is differentiable at z0, and that f of w is differentiable at w0 equals g of z0. Then the composition f of g of z, sometimes written like this, is differentiable at z0, and we have the following formula. Derivative of the outside, plug in the inside, derivative of the inside. Okay, so I'll prove this one too. So we'll break it into two cases, as Gamelin does in his book. So case one, let's consider the case where the derivative of g at z0 is non-zero. Then there is an epsilon greater than 0 such that g of z is not equal to g of z0 for z close enough to z0. So if this were not the case, right, then if for all epsilon, these things were equivalent to each other, less than epsilon, then you would in fact have a zero derivative. I'm trying to think if I can draw a picture here that might help, but I don't think I can. But the idea is if you write out the derivative, you have that first term on top, right? And if that guy is 0, then well, your derivative is going to be 0. Right? Okay. So this we just need this to allow us to write the following, which I'll mark with a star for later. We want to be able to write this as f of g of z minus f of g of z0 over g of z minus g of z0, and then g of z minus g of z0. So we've again creatively multiplied by 1, which we could not have done if g of z was equal to g of z0. Okay, so we assume that g is differentiable at z0, right? That's one of our assumptions up here. And that tells us, so that implies by one of our previous theorems that g is continuous at z0. What does that mean? That means that g of z approaches g of z0 as z approaches z0. Okay, so what does this thing go to? Well, we assume g is differentiable, so this term here is going to be the derivative of g, and this thing here is going to be f prime of g of z0, right? Because as z approaches z0, this g of z approaches g of z0. So this is like, well, we could write this another way, right? We could write this as, w equals g of z, w0 equals g of z0, right? And so when we take this limit as z approaches z0, what we have is the limit as w approaches w0 of f of g of z, sorry, that should be a w, minus f of w0 over w minus w0. That's what this first term is, right? That's because of this continuity property. And then we also have this limit left over. And this guy is g prime, z0, and this guy is f prime of w0, but remember w0 is g of z0. Okay, and that's exactly the formula that we wanted to show. Okay, so the second case is when the derivative of g is equal to 0. At z0. So how do we proceed here? Well, since we assume that f is differentiable at w0 equals g of z0, this tells us that this difference quotient must be bounded near w0 because f is differentiable. If it weren't bounded, then well, the limit wouldn't exist. So we can write that the magnitude of this guy is bounded above by some constant c. And for w small enough, so again, for some epsilon greater than 0, no, this is qualifying this statement, sorry. So this boundedness only holds near w0, right? Okay, so then we're just rewriting this. So this w is g of z, and this w0 is g of z0. So then this guy is bounded above by c times g of z minus g of z0 modulus. And this is again for, well, I'll just write for z near z0. Okay, well, what does that mean? Well, that tells me that the difference quotient for the composition of the functions, so this is the thing that we want to take the limit of to get the derivative, is bounded above by c times the modulus of g of z minus g of z0 over z minus z0. But this thing is the derivative of g. And what did we assume? We assumed that was equal to 0. So, well, I should say this approaches 0. And so what we find is that the derivative of the composition of f with g is equal to 0, as it should be when the derivative of g is equal to 0. So that's both cases, and so it completes the proof. Okay, so all these great rules that we have for real derivatives of real functions, they all hold, and things are looking great. Nothing seems too different so far. Now let's introduce the main object of study in complex analysis, which is the analytic function. So a function f is analytic on the open set U and C. So I'll just write open. If f of z is differentiable at each point of U. And the complex derivative f prime is continuous on U. So we'll see, later on in the lecture series that this last piece here is actually redundant. This part here is redundant. Actually, this first part, differentiability on all of U, is enough to guarantee that the derivative itself is continuous. This is called Gorsat's theorem. I think that's how you pronounce it. Which, doesn't really, it's not a theorem that's particularly useful for anything other than guaranteeing that we don't have to go through the nastiness of showing that a function is continuous. Which is I think that's a great thing. Okay. All right, let's continue. So we can write a complex function f as, well, let me write it this way first. The real part plus I times the imaginary part. But let me introduce some notation to make this look less ugly. So let's write u of z equals the real part of f, and v of z is the imaginary part of f. So then f is now u of z plus I v of z. Okay, so so recall that the differentiation in C is really restrictive, right? We talked about having to take this limit from any possible direction in a plane, not just the two directions on a line like you would for a real function. We can actually use this to our advantage to simplify the process of showing that a function is analytic. So first, let's simplify this notation a little further. So I'm going to identify u of z with u of x, y. So here z is going to be x plus I, y. So oops. So the idea is, well, z is a function of its real part and its imaginary part, and so u might as well just be a function of those two variables. Right? And we'll do the same thing for v. V of z equals v of xy. And what we'll show is that the derivative, so the complex derivative of f is related to the partial derivatives of u and v with respect to x and y. Okay, so we'll break this into two cases. So what we're going to do right now is derive what are called the Cauchy-Riemann equations. All right, so here, I'll write it down on the next sheet of paper. So we're thinking about f as a function of u, which is a function of x and y, plus v, which is a function of x and y as well. Okay, case one. So we'll use this technique that we used when we were deriving the showing that the complex conjugate map is not differentiable. We'll first take delta x to be real. Sorry, delta z to be real, call it delta x. Well, then the derivative at z is, well, this is now the limit as delta z goes to 0, but delta z is now the real delta x. F of z plus delta x minus f of z over delta x. And this is the limit. So we're going to plug in our u's and v's now. U of x plus delta x y, right? This is z plus delta x, which is equal to x plus delta x plus iy, right? Plus I v x plus delta x y minus u of xy minus I v of xy over delta x. So these two came from here, these two came from here. All right, and I will just break that into two limits. And now this is the part where I say, hopefully we've all taken, what is it, calculus 3? There's an I here. And know what these things are. So this limit here is nothing but the partial derivative of u with respect to x plus I, there's my I, and then this quantity is the partial derivative of v with respect to x. So the complex derivative of a function f, which can be expanded this way, is just the partial derivative of the real component plus I times the partial derivative with respect to the the partial derivative of the imaginary component with respect to x. And well, that looks mighty non-symmetric, right? Because we have these x's here, and we don't have the same thing, but we don't have any y's showing up. Let's say, well, they show up a different way. We can take delta z to go down the imaginary axis now. Okay. What happens here? Well, we get the limit as delta y goes to 0 of, so we'll do the same thing. We'll have f of z plus I delta y minus f of z over I delta y. And so what do we get at the end of the day? We get this limit as delta y goes to 0 of v of x y plus delta y minus v of xy over delta y minus I limit delta y goes to 0 u of x, y plus delta y minus u of xy over delta y. So where did this come from? Well, so this v and this u came from this f, right? And then this v and that u came from that f. And yeah, okay. Let's see, what do I want to say? Okay, so this thing here is nothing more than the partial derivative of v with respect to y. We have a minus I. Maybe I should say where that minus I came from. Give me 1 second. But this is the partial derivative of u with respect to y. So where did this guy come from? It came from multiplying both sides, or the top and the bottom, both by minus I. So this guy becomes 1. And then we get a factor of minus I, which maybe it's worth writing out the between step. So this is u of x, y plus delta y plus I v of x, y plus delta y. And then, minus u of xy plus, or sorry, minus I v of xy all over delta y. So the other I delta y, the other I is coming from here. So in the u case, we don't have an I there, and so we multiply top and bottom by minus I, and that gives us this guy. In the v case, multiplying the top and the bottom by minus I just cancels both of them. Okay, so we have these two expressions for the derivative of f, and so they must be equal. And so that tells me that, well, the real part of this guy must be equal to the real part of that guy. The imaginary part of this guy must be equal to the imaginary part of that guy. And so we come to the famous Cauchy-Riemann equations. So a function f, which can be written as u plus iv, is, if it's analytic, it must be true that the partial derivative of the real part with respect to x is equal to the partial derivative of the imaginary part with respect to y, and then derivative of the partial derivative of the imaginary part with respect to x is minus the partial derivative of the real part with respect to y. Okay. So these, again, are called the Cauchy-Riemann equations. All right. So we've shown that an analytic function satisfies the Cauchy-Riemann equations, and the natural question is the converse true? And the answer is a qualified yes. So let me write down the theorem. So let f equal u plus iv. Let it be defined on a domain D and C, where, so u and v are both real valued. Then f is analytic on D if and only if u and v have continuous first order partial derivatives that satisfy the Cauchy-Riemann equations. Okay, so it's a qualified yes on the converse because we do need the partial derivatives of u and v to be continuous. And this is not guaranteed by the differentiability of u and v, right? It's true that if a complex function is differentiable, then its derivative is continuous. That's Gorsatz's theorem, which we'll get to later. Not today, but another day. It's not true that if u and v are if they're differentiable with respect to each of their variables, it's not true in general that these partial derivatives are continuous. Right? And so we need to take this assumption into account. Right? So here's the proof. So the only thing we haven't shown yet is this converse. So all I'm going to prove here is the converse direction. So we apply Taylor's theorem, which tells us that u, oops, there should be a y. When we perturb it a little bit in both components, is u of x, y, plus the partial derivative of u with respect to x, delta x, plus partial derivative of u with respect to y, delta y, plus a remainder term, which actually only depends on the differences, delta x and delta y. So I should clarify when I say du by dx here, the thing that I'm evaluating this function on is xy. So when I write something like this, what I mean is du by dx with xy plugged in. Okay, so we're not done with Taylor's theorem. It also guarantees that this remainder term divided by the modulus of delta z, so that's just delta x squared plus delta y squared, take the square root of that. This goes to 0 as delta z goes to 0. Okay. So we have this fact, and similarly, whoops. Similarly, for v, we have v of x plus delta x, y plus delta y. So it satisfies the same thing. We're going to give this remainder term a different name. We're going to call it s. But again, this only depends on delta x and delta y. And we're again guaranteed that this remainder term divided by the modulus of delta z goes to 0 as delta z goes to 0. Okay, so that's Taylor's theorem, which just comes from ordinary calculus, right? Because u and v here are both real valued functions. So from this, it follows that well, we can write f of z plus delta z as f of z plus du by dx delta x plus du by dy delta y plus this remainder term. I'll just say it depends on delta z, right? Depends on both delta x, delta y, and that's the same as saying it depends on delta z. Plus I dv by dx delta x plus I dv by dy delta y plus I s of delta z. Okay. Okay, so this just followed from plugging in. So f is u plus iv, right? So plugging in for u and v. So now what we'll do is we'll apply the Cauchy-Riemann equations. Right? So we're assuming that u and v satisfy the Cauchy-Riemann equation and that their partial derivatives are continuous. Right? And we're trying to prove that f is analytic because of that. So what we get from the Cauchy-Riemann equations is that f of z plus delta z is f of z plus du dx plus I dv by dx delta z plus, well, the remainder terms. Okay. So let's see, where do I want to go from here? I want to divide that delta z out. Okay, so I'll try to put this right here. So we're going to divide by the delta z. Well, first we want to subtract this f of z out, right? We're trying to get the difference quotient on the left-hand side. Okay, so that's going to remove this f of z. And then I'll divide everything by delta z. So that's equal to du by dx plus I dv by dx. I no longer need this parenthesis. Plus r of delta z over delta z plus I s of delta z over delta z. And now I take the limit as delta z goes to 0. And if it exists, then I know that f is analytic because, well, it's complex differentiable in the neighborhood D. So I take the limit, and from Taylor's theorem, I was guaranteed that both of these quantities go to 0. And so I'm left with this guy, I should say goes to. And so, well, I know that the partial derivatives exist and are continuous, and so, well, the limit exists. And so f is analytic on our domain D. And that completes the proof.
So I wasn't paying attention.
So the Cauchy-Riemann equations are almost sufficient. You also need this continuity of the partial derivatives, but if you have that, then yeah, it's equivalent to analyticity. Okay, so let's just do a few examples, and we'll call it a day. Oh, actually, there's a couple more results I do want to prove, but they're easy. Let's just do one example then. So take this function, the exponential, we'll see it a lot. This is e to the x plus iy, which is e to the x, e to the iy, which we can write as e to the x cosine of y plus I e to the x sine of y. So this is Euler's formula, right? E to the I theta is cosine theta plus I sine theta. And so what we have is that our u as a function of x and y is just e to the x cosine y, and v as a function of x and y is e to the x sine of y. So to check that this guy is analytic, all we have to do is show that these guys satisfy the Cauchy-Riemann equations and have continuous partial derivatives. Well, the partial derivative of u with respect to x is, well, that's just e to the x cosine y. And that guy is definitely continuous. It's a product of continuous functions. Okay, and then this is equal to partial derivative of v with respect to y. Okay, so first equation checks out. And partial derivative of u with respect to y is equal to minus, where's my u? Here it is, minus e to the x sine of y. And this guy is also continuous, right? Continuous function, products of continuous functions are continuous. And then this is minus dv dx. So both of my Cauchy-Riemann equations are satisfied. All my partial derivatives are continuous. This tells me that f is analytic. In fact, I didn't even specify the domain. Well, this guy is defined on the entire complex plane, right? And well, we had no care for the domain, so this must be true everywhere. So there'll be a name for that. Functions that are analytic on the entire complex plane are going to be called entire, but I'll get to that later. Okay. So let's do a couple of examples of theorems you can derive using the Cauchy-Riemann equations and also showing that analyticity is pretty powerful. So if f is analytic on D and C, so we assume D is some nice domain, it's open. Maybe I think we want it to even be path connected, but I won't focus on the details there. So if f is analytic on D and its derivative is 0 on D, then f is constant. So this is obvious and maybe not obvious. This is something we're familiar with from real analysis. Derivative of a function being 0 implies that it's constant, right? So let's just show that this still holds true. So f analytic implies that the Cauchy-Riemann equations hold. But we also have the assumption that f is 0 on D. And so this implies that, so remember, we can write f prime of z as du by dx plus I dv by dx. We can also write it as dv by dy minus I du by dy. Do I have that right? Let's see, here should be equal, yes, okay, good. Okay, so if this guy is 0, that means both of these guys are 0. And so, well, everything here must be equal to 0. So this tells me that du by dx is dv by dx is dv by dy is du by dy, which is equal to 0. So this guy tells me that u can only be a function of y. And then this guy tells me that, in fact, well, no, it's not a function of y, it's just a constant, right? So those two imply that u is constant. This guy tells me v is a function of only y, and then this guy tells me, no, in fact, it's constant. And so putting those two things together tells me that f is constant. And then the last thing I want to show is this very nice theorem. So that last guy just told us that something we thought should be true based on real analysis was true. And this guy is maybe a little surprising. So if you have an analytic function and it's real valued on your domain, then in fact it's constant. Here's the proof. So f is analytic, so it satisfies the Cauchy-Riemann equations. So by the Cauchy-Riemann equations, we have that du by dx is equal to 0, equal to dv by dy. Yes, yeah. So this is coming from, again, the thing I wrote down earlier. F prime of z is equal to du by dx plus I dv by dx, du by dy minus I dv. I got that backwards, dv. And then this one should be u. Okay. So we're assuming that the function is real valued, right? So actually these v terms are 0. That's what real valued means. So that guy is 0, that guy is 0. And so what I'm left with is, well, if my Cauchy-Riemann equations hold, that tells me that du by dx is equal to dv by dy, which is 0, and then dv by dy is equal to minus x. Sorry. Oh, wait. I think I wrote something wrong. I wanted to put a u here. Okay. And so the other thing it tells me is du by dy, which is equal by my Cauchy-Riemann equations to minus dv by dx, is also equal to 0. So that's where this comes from. So that tells us that, well, u must be constant, right? Because both of its partial derivatives are equal to 0. But f is real valued, and so v is 0. So the only thing it's a function of is u, and so that implies that f is constant. And that completes the proof. So we have this, maybe our first, I don't know, Cauchy-Riemann equations are kind of surprising themselves, but this is maybe our first theorem which is surprising outside of that. So if you have a complex function which is analytic, which just means that it has a derivative in some neighborhood, and if it happens to be real valued on that neighborhood, then in fact it has to be constant. Okay, so I'll go ahead and stop there, and I'll open up the floor for questions.
So I'm kind of confused. I think you might have meant to write dv dx and dv dy is equal to 0, since v is, we're assuming, is 0. Like right under the Cauchy-Riemann equations? Yes.
Yeah, so you're correct that those are both 0 by assumption, right?
Yes.
Because f is real valued.
And
But
then
by
we
the
get
Cauchy,
that. Yeah.
yeah, we get this from that.
Okay, yeah, maybe I was just like, the order of reading makes it seem
Yeah,
like
sorry,
it's going the wrong direction.
I wrote it
Okay,
down first, and then I tried to derive it as like an aside.
Yeah, for sure,
Yeah.
for sure.
Yeah.
And then whenever you were proving analyticity by the Riemann equations,
Yeah.
I got I maybe like did not pay attention. One of the equalities kind of confused me. It was like 2 or 3 pages back. F of z plus delta z computation.
Find it. Have this guy, and then I think it's after that, right?
I think it might be right after that.
Where are you?
Or it might be right at the bottom of this page. I don't know. Could be the next page though. Notice this page. Yeah, the very last expression. Can you maybe explain how that follows from the previous line, or are they not really supposed to follow?
So this was from the Cauchy-Riemann equations.
Oh, okay. And so you're just substituting the expressions.
Yeah. So du by dx equals dv by dy.
Okay, cool. That makes a lot of sense now. So at first I was just like doing the product of delta z, and I'm like, what's going on here? But then yeah, that makes a lot of sense.
No worries. Okay. Any other questions?
Yeah, I may have one.
What you got, Christoph?
Uh, so a domain is a open set subset of C of the complex plane, but is there another uh, condition on what you call a domain?
Yes, I wrote it down. Let me find.
It doesn't need to have like positive measure. Like what if it's just like the real axis or something?
So Gamelin's book is not that advanced. It's not going to talk about measure theory, but uh,
I think it has to
it's
do with one piece like connects, right?
yeah, 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 yeah. So
Because if the function is constant on the domain, it could be in two pieces, right?
right. So it's a domain if it's open
Right.
and if any 2 points,
Can be connected.
yeah, can be
As connected.
connected, not by a line, but like a broken
Yeah.
by a
Path.
broken line.
Okay. Okay.
Yeah, yeah.
Yeah, because
So
the constant thing, the constant function may be like piecewise constant, in fact, so that would not work, right? It could be two pieces of the not connected pieces of the plane, and then
right, right.
the function would be constant on each piece, but not the same constant.
Yeah, that's exactly
Right,
right.
right.
Yeah. So
Okay, okay. I get
I
it.
I did not go into enough detail there, I think,
Yeah,
but
no, no, it's fine, but I mean, it's just how you define a domain. That's
yeah. So we essentially want path connectedness, right? So
right,
we don't
right.
get this disjoint union
Yeah,
of things where the function
yeah,
is constant on
Yeah,
each,
what's
but
a broken line in this definition?
it's. I'll just draw you a picture, and
Yeah.
I think you'll get it. Just something like that.
Oh, just like these sort of line segment things.
Yeah, just like a union of line segments where they're
Yeah.
connected.
And then what example do you know of a function in two variables that is differentiable, but its derivative is not continuous? So that's what
Ooh,
we're assuming for Cauchy-Riemann, right?
yeah, yeah, yeah.
There's something weird, right? You can't make that happen in 1D, right?
Well, you can certainly make it happen in 1D, right? Uh,
Because I thought it would just not be differentiable at one point then.
hang on. Trying to come up with an example on the spot.
Yeah.
Do you have a good one handy, Christoph?
um, I remember this xy over square root of x squared plus y squared or something like that. That definitely does not work. Or I'm not sure about the expression, but there is this simple fraction
Mhm.
that at 0, 0 it behaves weird because I don't know. I'm not
Yeah.
sure, but
But
Oh,
it's
oh,
something in two variables, not just
I
one.
see. I see. So,
oh
yeah,
yeah, in one variable. Okay.
yeah.
So you want the derivative to exist and not being continuous? Is that
Yeah.
Yes,
at
yes.
every point or at just one point?
I was
Uh,
just thinking of a like something that would fail Cauchy-Riemann in maybe a 1D case, so I can think that way.
yeah, yeah. So you really only need 1 point where it fails. Um,
I mean that's I'm sorry, that's I mean absolute value is not differentiable at one point, but and it's also not continuous. But is can it
yeah.
be differentiable everywhere but not continuous?
So the function itself is continuous, right? But we're asking about whether or not the derivative is continuous.
Yeah, right.
Yeah.
Exactly, exactly.
Um, hmm.
Seems like it has to be a 2D thing or a pathological weird construction or something.
Yeah,
Like not even possible. I don't even
I
know.
think probably a piecewise function, cleverly constructed would probably work. I can't think of one like an elementary function by itself that does this, but maybe we could define like f to be I don't know, x for x greater than or equal to 0, and then maybe x squared for x less than 0. Uh, let's see, does that work out? What would our derivative be? F prime would be
Oh, then
1.
at 0, I guess it's 0. That seems
Yeah, then yeah. So there's an
not
example.
continuous. Well, this is continuous.
Well,
Oh,
the
it's not.
derivative
No, not. Yeah, yeah.
it's not at 0. Yeah.
Not 0. Yeah, yeah. Okay. There we go. For some reason, I was just thinking on absolute value. I was always thinking corners, and I'm like, that's the wrong thing. This is perfect.
Yeah. Okay.
Can I ask another question? Sorry.
Sure.
So one of the two Cauchy-Riemann conditions tells you exactly that df over dz is df over dx, right?
Yes. Yeah.
I mean, isn't it like, do you have any, like,
Any commentary?
yeah.
Other than it's just kind of cool.
Yeah, I mean,
So
so
so what was interesting about that derivation was it came from the restriction of the limit,
yeah,
right? It had to be it had to exist and be equivalent in every direction, right? And when we came this way, what we found was that the derivative was du dx plus I dv dx, right?
which is
So,
df
so
dx.
basically, yeah, basically df dx, right?
Yeah. Okay.
So
Oh,
we're right
okay,
there,
okay. Yeah, obviously.
right? And then from this direction, we saw that was actually also equal to df dy.
With the I or something,
Uh,
with minus I,
yeah, what is it?
minus I.
Complex
Yeah, something.
commutative.
Yeah, something like
Yeah.
that. Yeah.
So
Okay, I get it.
it's just it's a product of this restriction, and you can go from other directions if you want to, and
Yeah,
you'll get other equations that hold, but
yeah.
um,
So it says basically that you just need to take the derivative in one of the variables. I mean,
yep. Yeah, that's right.
I mean, these are really nice functions, is the takeaway.
Yeah, I mean, analyticity is a very strong restriction. Yeah. Okay, any other questions?
I have a like off the recording question.
All right, I'll stop it. Stop share.